All right, good afternoon, everybody. My name is Anthony, and this is Dan, and we are going to be giving a presentation, as the professor just said, on the prediction of unsteady aerodynamic behavior of flapping wing micro-air vehicles. So to start this presentation off, I'll give a quick overview of what we'll be covering. So we'll start with some basic theory and the assumptions that we'll use in steady state or thin airfoil theorem. We'll then move on to the introduction for unsteady aerodynamics and unsteady thin airfoil theorem. We'll then go over a qualitative analysis of our MATLAB program and thin airfoil unsteady thin airfoil theorem. We'll then move on to build that MATLAB program, that script structure. After that is done, we'll go over the specification requirements that we set forth for that program to be determined successful, go over our results, some of the optimization we did, some of the numbers we played with. And then we'll give our conclusions and some recommendations for future projects.
I think I was saying, it would be important to know some assumptions we've had. The first assumption we've had is the viscid flow. That is the ability to ignore friction and transfer analysis. The second assumption we have is compressible flow. That simply means that density is constant throughout the analysis. We are able to assume that density is constant because the maximum velocity of a flapping wing is approximately 15 meters per second. And looking at the chart, that's well within that blue shaded region, and that is acceptable range to use the compressible assumption. Moving on, our third assumption is superposition. In math, that simply means we are able to add vectors together. However, in aerodynamics, that is the ability to add different flow types together. Pictured here is just one type of flow, which is uniform flow, but there are numerous others. With the ability to use superposition, that means our analysis is we'll be using a linear equation, which will be proven to be useful later. Our last assumption is the cutter condition. That means that at the trailing edge of an airfoil, velocity is 0. The vortex sheet is also 0. With the four aforementioned assumptions, this leads to a theory in aerodynamics known as thin airfoil theory. And thin airfoil theory utilizes Bernoulli's equation, which will be used in unstable.
Right. So as Dan explained, for a thin airfoil theory, we'll be using the assumption that the flow is viscid and compressible. These assumptions will also hold true for its unsteady counterpart. The cutter condition still needs to be satisfied, so at the trailing edge of this thin airfoil seen in this figure, there will be no vorticity. However, since we are adding shed wakes into the wake for an unsteady thin airfoil, we will need to use the conservation of circulation, or Kelvin's theorem, which states that the time change magnitude, or the time rate change of the magnitude of a given vortex is equal to 0. This will be used to relate the trailing edge vortex, which we will talk about later, to the wake vortices. All right, so a quick qualitative analysis for unsteady thin airfoil theory. So again, we will have vortices that will be bound to a chord line of a thin airfoil, but there will also be vortices present into the wake. The lift on this thin airfoil will be calculated via the Biosphere law seen there. At this point in time, the only known value in this problem is the imposed motion dictated by the kinematic equation seen above, which relates the position on the airfoil to the pitching motion given by alpha. In order to solve for the aerodynamic loads on the thin airfoil, we will need to solve for the infinite number of unknowns of the vortices bound to the thin airfoil. We will do this by discretizing this thin airfoil into n panels with one extra element for the trailing edge, where this element will be shed into the wake at each individual time step. These shed vortices will follow the free stream, and the free stream is determined by the Biosphere law as well.
Continuing the qualitative analysis, the first step is to look at what happens when time equals 0, or when no time is passed. As indicated in the figure, there's still no wake vortices yet. At t equals 0, it is a steady state case. Steady state case simply means that the velocity vectors do not change. That equation you see there, v perpendicular to 1 equals v motion 1, that equation satisfies the cutter condition and the conservation of circulation that Anthony mentioned earlier. With t equals 0 looked at, it is now smart to look at when some time has passed, or when t equals delta t. Here, the trailing edge when t equals 0 is now in the wake, denoted here as gamma wake 1. That value is known, as Anthony mentioned earlier. The only thing we need to solve for is the bound vortices, and that is repeated until the final time step is concluded, and that could take either a long time or a short time. And here, this is just some important variables that we have in our program. K is reduced frequency. That's the equation omega times v divided by the free stream velocity. Free stream velocity here is 5 meters per second. Density is 1.225 kilograms per meter cubed. N is number of panels. Pitching motion is a kinematics of an airfoil. That's the up and down motion of an airfoil. And then the fuzzy motion is the vertical displacement. Here at 0, you can see that those values there.
All right, so after our initial parameters have been set for a program, we will need to define the Biosphere function, which will be called separately. So again, we'll be using the function seen here, where the induced velocity is calculated from the relationship between a control point P and a vortex V and the distance between them, where that distance is calculated by a simple trigonometry. So into our MATLAB program, you see this function takes two sets of data, the XY coordinate of the control point and the XY coordinate for the vortex point. All those variables dx, dy are calculated here. In order to make sure this function doesn't loop infinitely, we set a simple cutoff for R2, because as you can see, you reduce R2 as a denominator, so that for 0, this will loop infinitely and produce no results for us. So next, we will define the geometry of these individual panels, which will be taken by the Biosphere function. The control point P will be located at the 3/4 stroke point, which is traditionally where the pitching is measured for a thin airfoil. The bound vortex will be placed at the quarter position, which is the aerodynamic center for a thin airfoil. Implemented in the MATLAB, you see the for loop goes from panel 1 to panel N. The X-bound position is at the quarter point, defined there, and the control point at the 3/4 stroke point. The angle at each individual panel is set equal to 0 because we're not considering camber for this simulation. And the normal vector for each panel is calculated again. At the trailing edge, we are going to set a position for the trailing edge vortex, 2b, which is 2 times the semispan, which is just at the trailing edge. Next, we will move on to calculating the normal velocity, which is the part of this program. The left-hand side of this linear relation, which is the normal velocity at each individual panel, is related to the kinematics at each individual panel, which was defined earlier. This normal velocity will be calculated by a Biosphere law. It is important to note that the Biosphere function did not take a magnitude for any of the vortices, so this will produce a unit vector value. And before we move on, we'll need to add the effects from the wake, which is calculated much the same way as the bound vortices. You can see here it uses the same function. We just add on and multiply it by the wake magnitude, which is a known quantity. So since the bound vortices are still unknown, we will create an influence coefficient matrix called A. It is an n by 1 by n by 1 matrix, which is found from the Biosphere law. And we will then subtract the effects from the wake onto the right-hand side and then solve for the bound vortices magnitude. And you can see here, in order to initialize the influence coefficient matrix, we just call the Biosphere function using the control point and the bound vortices point. It's also important to note that the very last row of this influence coefficient matrix is set equal to 1 in order to satisfy the conservation of circulation.
Now that we have established the matrix coefficient and also the geometry of the airfoil, it is not important to know how the airfoil moves. This was mentioned earlier. Like I said, there's two major categories. Plunging, like I said, the vertical displacement of the airfoil, but that is not included in our analysis because that was h equals 0. What is included is pitching motion. That's just the up and down motion of the airfoil. Here, alpha equals alpha naught plus a times sine omega t. That's the pitch angle equation. And if you were to take the time derivative of that, you get alpha now, as shown here. We did this for plunging motion just to show that it can be similarly done as well for plunging motion. Recall the velocity motion equation introduced beginning of the unsteady domain, it was velocity motion equal normal velocity times the quantity of the alpha angle of attack minus the control point. In addition to that, with the kinematics equations in mind, this is the velocity motion in the x and y coordinate system. That's what it leads to. Here, this program, this is showing that there is now two major contributors in the lift generation. One is the airfoil motion, which was, in this case, is pitching. And the second is the weight. That's shown here on the right-hand side with the two contributors shown there. Now that we know the strength of the bound vortices on the chord length, we can now calculate the aerodynamic loads. Recall that I mentioned Bernoulli's equation. This equation, the first equation here, delta P, that is Bernoulli's equation in the unsteady domain. That simply calculates the pressure difference on the upper and lower surfaces. Now that we know the pressure differences, we can now calculate the forces in the x and y direction. Now that we know the pressure difference and the forces, that lets us to able to compute lift and CL for the airfoil. As Anthony was mentioning earlier in the matrix portion, what we have done, this is true for bound vortices, but this analysis is also true for the weight analysis. Going back 2 slides, if you look at the velocity motion x, that velocity motion equation for weight as well is identical. That does not change. What does change, however, is the velocity motion y. So the first term, the u and sine alpha are the same, h dot and cosine alpha are the same. The third term changes slightly, but in a major way. The slight change is YCP. YCP denotes the y coordinate, the control point. In the wake analysis, YCP becomes the YW, which similarly means the y coordinate a little bit. Moving forward, this is just showing you the different effects on lift. Bound vortices and the wake vortices.
All right, so now that we have the program script structure established, and before we go over some results, we'll go over the specification requirements for this program. The first one that we set was that the simulation runtime must not exceed the total time being simulated. That means that the program is running in real time. The results must be within a 5% average and a 10% maximum error in comparison to Theodorson's method, which is another thin airfoil theory that we're using in this program. Ease of use either through simple simulation calculations or from use in a control system for some sort of flapping vehicle. So for our initial results, for a reduced frequency of 0.1, our appreciable velocity of 5 meters per second, and a maximum pitch angle of 5 degrees, we can see that the average error is 5.6% and a maximum error of 8.83%. And moving on to other reduced frequencies, we see that as we raise the reduced frequency, which is a measurement of the airfoil's unsteadiness, that the Theodorson's and the unsteady vortex lattice theorem converge, the error between them lessens as you raise the unsteadiness of the problem. You can also see a phase shift between the two as you increase the reduced frequency. You can see that the initial value for the unsteady vortex lattice theorem is quite a bit higher than Theodorson's, which we assume to be from the initial state from our unsteady vortex lattice theorem, which is a steady state thin airfoil theory case. So looking at some numbers for the error between them, we see that, just like the graphs indicated, the average and maximum error reduced quite a bit with increased reduced frequencies. However, the run times, as you reduce the reduced frequencies, grew exponentially. It's not listed here, but for a reduced frequency of 0.1, run times exceeded 18 hours. So why was this the case? In our program, again, we defined the reduced frequency by this equation. The final time, the amount of time simulated in the program is determined by 4 pi divided by the angular frequency. So for a k value of 0.1, it simulates about 12.5 seconds. And each individual time step for this program, which determines how many data points will be in each results is determined by the spatial and temporal matrix in here. So for this instance, there are over 2,500 time steps, so 2,500 different data sets. And if you remember, we mentioned in the qualitative analysis section for the Biosphere function, each individual time step, we will be introducing a new vortex into the wake. So every time step, the complexity of this program increases quite a bit.
Wanting to improve our runtimes, the thing we mutually agreed to change was the number of panels. Previously, the number of panels was 40. Here it's 35. However, there is one exception, which is this graph up here. This graph was when reduced frequency was 0.05. We changed this to n equals 10, because if you remember, when the reduced frequency of 0.1 was chosen, number of panels of 40 was 18 hours. So that was our way to reduce the runtimes as much as possible. But as you can see, it's comparing unsteady vortex lattice theorem comparing to Theodorsians. There's a valid way to predict lift generation. Moving forward, so this is with the new parameters n equals 35. This, for instance, looking at when reduced frequency was 0.5, this runtime, I'll just go back. I'll show you. I'm looking at 0.5, about 609 seconds. With the optimized number, 150 seconds. But so that dramatically improved. But looking at the average error, it's still below 3%. So we were happy with the results we had. Here it's the weight behavior. Left, they're similar graphs. They measure the same thing. On the left is the final time of 3 pi over omega. On the right is 4 pi over omega. On the right, the magnitude is much larger. It's about 1. The left is about 0.2. With an increased final time, the runtimes will be most likely increased.
All right, so from the data that we collected, we can see that the use of the Biosphere law prevents longer simulation times, and this can be remedied by separating the problem into 2 separate domains, one the inner domain, one the outer domain, where the inner domain still uses the Biosphere function, but as the vectored weights pass out of this inner domain, they will follow a simple sinusoidal trajectory. Another observation we had is that the unsteady vortex lattice theory script and Theodorsians have an opposite trend with respect to K, which indicates that this script is most applicable for higher reduced frequencies. Questions?
Difference between Theodorsian's theory, your methods, and you explain why it's different. Which one is better?
Correct. Well, Theodorsian's theory was originally used to measure the lift being produced by a thin airfoil flutter analysis. And what's special about Theodorsian is that it doesn't involve, as far as I remember, the wake convection. And it also, at the initial time step, doesn't include a steady state case. So those are the main differences between the two.
Question. Share with us what you need.
Probably at the beginning of the project, we were focusing on predicting lift just from observing how different birds and insects flap their wings, and how you translate traditional classic aerodynamic theory like thin airfoil into that. And one of the initial assumptions is that you just oscillate the wing, and we figured out through research that one of the main drivers of lift in this regimen of flight is the introduction of wake vortices, which will induce a velocity on that wing, which will enhance lift, which is quite different than steady aerodynamics, where oftentimes those wake vortices induce a negative velocity and decrease the amount, especially for three-dimensional wings. So it's the most interesting thing that we found is that for wings that are extremely small with extremely small Reynolds numbers, the trend sorts of looks somewhat opposite in comparison to their steady-state counterparts. So that was the main thing.
Your result seems showing some instability.
I'm sorry?
Instability. No.
Instability?
I didn't.
I don't think that program is that safe.
Okay, we give parts.